last time we looked at when the class number is 1 for real quadratic fields for trivial reasons. Trivial reasons meaning that the Minkowski bound is less than 2. So, this time we try to do the same for imaginary quadratic fields. So, let K be an imaginary quadratic field, okay. So, n is 2, R1 is 0, R2 is 1, right. Then the Minkowski bound is equal to 2 factorial by 2 square into 4 by pi into square root of mod dk, and I want this to be less than 1. So, this is less than 2. So, this is less than 2 if and only if mod of the discriminant is less than pi square, right, which is yeah, I do not know, this means that yeah, this is less than, certainly less than 11. So, let us go with that. So, this means what are the possibilities for dk. So, remember dk is a dk is negative and it has to be 0 or 1 mod 4. So, the first such thing is minus 3, right. So, this indeed is a discriminant of the following number field. So, this is k q square root of minus 3. The next possibility is minus 4, and again this indeed is a fundamental discriminant for this number field. Then dk is minus 7, and again this is the following thing. So, right. And lastly, we have dk is minus 8, and again this is for this number field, sorry, minus 2. Okay. All right. So, if k is equal to q square root of minus 3 or q square root of minus 1 or q square root of minus 7 or q square root of minus 2, then class group of k is 1, okay, is trivial. But this is by no means the complete list of trivial class groups. In fact, so this was again this is a theorem of Hegner, I guess, plus other people, and this was conjectured by Gauss again, right, that CL of k is 1 for k equal to q square root of m if and only if m is the following, one of the following discriminants. Maybe I will not write m and I will write d as dk as usual. So, dk less than 0 if and only if dk is equal to minus 2, sorry, minus 3. So, he wrote down a list of 11 things: minus 2, minus 4, minus 7, minus 8, minus 11, minus 19, minus 43, minus 67 and minus 163. If your discriminant, negative discriminant for the imaginary quadratic field is anything other than these, the class number is 1. And in fact, again it is a theorem, I think, due to Davenport and Heilbronn. Yeah, maybe let me write it like this: Davenport. Yeah, I think there is somewhere Baker's name should also go in, but I am not sure exactly where. So, this says that the order of the class group goes to infinity as as mod of dk goes to infinity. Here dk is negative all the time, right. So, the class group keeps increasing with the, this is roughly how it can be stated. There are more precise versions of this. Okay. So, unlike for real quadratic fields where you expect infinitely many real quadratic number fields with class number 1, it is known that this is not the case for imaginary quadratic fields, and in fact the class number keeps increasing as the mod of the discriminant keeps on increasing. Okay. So, let us look at some examples then. Okay. So, first example, let me show you that the class number can be something different than 1 if you if your even sort of when the discriminant is class number can be 1 even if the discriminant is even if the Minkowski bound is bigger. But let us yeah, okay, let us do some of those examples. So, let us say k is q square root of minus 11, right. So, what is minus 11 is 1 mod 4, right. And so, the discriminant is again minus 11, right. And so, Minkowski bound is 2 factorial by 2 square times 4 by pi into square root of 11, and square root of 11 is certainly less than 3.5. So, I get something like less than 7 by 3, let us say, which is certainly less than 3. So, all I need to do is to find what is O 2 times OK, and so I just look at x square plus 11 congruent to 0 mod 2, right, and so this is same as x squared plus 1. Sorry, no, I should not look at this equation, right. I should look at the equation, sorry, this is not the right thing. OK is z square root of 11, square root of minus 11, 1 plus square root of minus 11 by 2, right. And so, if we want to find out what the minimal polynomial of this is, so let me call this alpha. So, x is 1 plus square root of we have done this before. So, I am just kind of recalling that. So, alpha minus half is equal to, so square is equal to minus 11 by 4, and I can write this as alpha square minus alpha plus 1 by 4 plus 11 by 4 is equal to 0. So, alpha square minus alpha plus 3 is equal to 0, right. And now, what I can do is I can just right. So, I can just consider x square minus x plus 3, which is congruent to x square plus x plus 1 mod 2, and you see that this is irreducible mod 2, right. So, this is a prime ideal, which means that it is also principal, right. So, hence the class group of K is trivial, right. So, even when the Minkowski bound is bigger than 1, of course, you can get lots of trivial classes. Okay, so that's our first example, but we are going to do lots of examples and in the process learn lots of different techniques on how to do these computations. Okay. So, let us look at k q square root of 82, right, and so 82 is not congruent to 1 mod 4, right. Hence, the discriminant is 4 times 82, right. So, whatever that is, so 238, 328, sorry, 328, right. And so, if you look at the Minkowski bound, this will be 2 factorial by 2 square times square root of 328. So, this is half of square root of 328, and what is that? So, that is roughly 18, 19 square is 361. So, this is less than 19 by 2, which is certainly less than 10, right. So, we want to find out how so we want to find out how 2 OK, 3 OK, 5 OK and 7 OK factorize, right. And so, what we are going to do is we are going to look at the polynomial x square minus 82, right. So, x square minus 82 is so x square minus 82 is congruent to x square mod 2, and so 2 OK is just some prime square. I mean, this is, we knew, we should know this anyway without doing this computation, but nevertheless x square minus 82 is congruent to x square minus 1 mod 3, right. And so, what is that? So this factorizes as product of x plus 1 into x minus 1 mod 3, right. So, 3 OK, this is some p 3 times p 3 prime for two distinct primes in OK, and x square minus 82 is congruent to x square minus 2 mod 5, and this is irreducible. So, 5 OK is a prime, and so we do not have to worry about that. X square minus 82 is congruent to, so I am looking at it mod 7 now, which is x square minus 5 mod 7, and 5 is not a square modulo 7. So, 7 OK is a prime. Okay. Okay, so now we know that CL of k is generated by class of P2, class of P3 and class of P3 prime. We know that P2 square is 1, and we know that P3 is equal to P3 prime inverse, right? They are inverses of each other. Okay, so so what do we do next then, right? So that does not tell you much about, I mean it tells you that there are, so CL of k is generated by two of these, let us say P2 and P3, right, and P2 square is 1. But beyond that we do not know much, right. P3 could have very large order, we just do not know. So what we are going to do is the following, we are going to look for norms of some elements in, so we look for norms of some elements in OK, which is simply z square root of 82, that are divisible by 2 and 3, right. So, if I have a plus square root of 82 times b, then norm of this is equal to a square minus 82 b square, right. So, what you do is you look at sort of norms that are small and divisible by 2 or 3. So, for example, I mean this equation tells you that you should look at a bigger than or equal to 10. So, let us just look at 10 first. So, you look at norm of 10 plus square root of 82, right, and this is 18, which is equal to 2 into 3 square. But you see that 3 does not divide 10 plus square root of 82, right. You cannot write 10 plus square root of 82 as 3 times a plus b square root of 82 for any a and b, that is clear. So, only one of P3 and P3 prime divide, so sorry for the handwriting, P3 prime divide 10 plus square root of 82, because if they both divide then 3 will also divide. So, without loss of generality, say that P3 divides 10 plus square root of 82, right. So, what this means is that 10 plus square root of 82 is equal to P2 into P3 square, right. P2 will only appear once, because in the norm of this element 2 appears only once, right. So, what this means is, so hence P3 square is equal to class of P2, right. I mean it is inverse, but we know that this is same as this. Okay. So, hence CL of k is generated by P3, the class of P3 only, and P3 to the 4, which is same as P2 to the 2, is identity. Okay. So, hence the class group of k is isomorphic to Z mod 4Z. So, it is a cyclic group of order 4, right. Sorry, not quite. If P2 is not principal, sorry about that. So, yeah, it is not quite finished. If we have to know that P2 is not principal, it has order dividing 4, but P2 could be principal. So, let us say if P2 is a plus square root of 82b, then norm of a plus square root of 82 times b, this will be equal to plus or minus 2, right. But this thing is a square minus 82b square, which is equal to plus or minus 2. Right. So, I want to say whether this has a solution or not, right, and in this particular case it is not hard to do. Okay. So, normally what I would do is I would look at things modulo prime factors of 82 and then see that there is no solution, but that does not work in this case. So, so maybe it works in some cases, but you see 2 is a square modulo 41. So, so that will not work. So, what we are going to do is we are going to say okay, P2 square will be generated by a plus square root of 82b, square, right, but this is also generated by 2. So, hence 2 is equal to a plus square root of 82b times u, where u is a unit. So, this should be square, where u is in OK cross, right. So, it is and if you take norms of both sides, you know, norm of this is 4, norm of this is also 4, and so norm of this will be 1, right. So, norm of u will be 1. So, it can't be minus 1 is what I am saying, because of the way it is defined. Okay. So, I have told you how to find fundamental units. So, earlier we have seen, we have seen how to find fundamental units in real quadratic field, right. So, we just find sort of x plus square root of 82 y such that norm of x plus square root of 82 y is plus or minus 1, and y is smallest possible positive number. Positive integer, right, in this particular case. And so, what works in this case is x is equal to 9 and y is equal to 1. So, if you look at 9 plus square root of 82 and you look at norm of this, then this is minus 1, right. Okay. So, but norm of u is 1, which means, right. So, u is in the group that is generated by this. So, u is 9 plus square root of 82 time to the power k for some k in z, right. But norm of u is 1, hence k is even, right. So, I can write, so then 2 is a plus square root of 82 times b into 2 to the power 2l, but I can absorb this inside, sorry, this should be square. So, I can absorb this inside and I can write this as u to the l square. So, I take this as a 0 plus square root of 82 b 0, right. So, 2 is a plus square root of 82 b 0 square, which is simply a square, a 0 square plus 82 b 0 square plus 2 times square root of 82 b 0, right. This implies that b 0 is 0 and a 0 square is 2, which is a contradiction, right. So, these computations can get quite involved because there are roots of unity, fundamental units. So, the group of units is infinite, right. If the group of units were finite, we would just have to do some finite computation. So, you see already in the first non-trivial example that we have seen. So, what is the answer? Hence, class group of K is isomorphic to Z mod 4 Z, right. So, we had to use information about fundamental unit. So, let us look at another example where you do not have units, and you will see the difference already that you do not have to work as hard, right. So, again the n is 2, R1 is 0, R2 is 1. So, the Minkowski bound is equal to 2 factorial by 2 square into 4 by pi, 4 by pi into Yeah, so minus 14 is not congruent to 1 mod 4, right. So, dk is minus 56. So, this should be 56, right, and square root of 56 is certainly less than 8, right. So, I can then do this as 2 by pi times 8, less than 2 by pi times 8. So, this is 16 by, so maybe less than 16 by 3. Usually these crude estimates are kind of enough to do, but I think we can do better this time. So, let us try to let me sort of keep it as it is. So, this is 2 yeah. So, 2 times square root of 56 by pi, and this turns out to be roughly yeah, something like 4.8, which is less than 5, right. So, it is certainly less than 5, and so all we need to do is to factorize 2 times OK and 3 times OK, and again the polynomial that I am interested in is x square minus 14. So, this is P2 square as usual, right, because 2 divides the discriminant, and this will be, so if I look at this mod 3, then this is x square minus 2, what, yeah, x square plus 14, sorry, x square minus 1 mod 3, and so this is P3 times P3, P3 times P3 prime, right. Yeah, and so again it is the same kind of thing that CLK is generated by P2, P3 and P3 prime, but P2 square is identity and P3 is same as P3 inverse. So, I can forget about this generator, right. I can forget about this generator, right. And then again I can look at yeah, and I can ask whether, so P3 P2 is principal. So, if P2 is alpha for alpha of the form a plus square root of minus 14 b, then a square plus 14 b square is equal to plus or minus 2, and this has no solutions. This has no solutions. Hence, P2 is not principal. Similarly, P3 is not principal, right. Then we look at other things. So, what you do is you consider norm of 2 plus square root of minus 14. This is again 18, 2 times 3 squared, and so as in the previous example, this ideal generated by 2 plus square root of minus 14 is P2 times P3 square, right. So, hence P3 square is same as the class of P2 inverse, which is same as the class of P2, and I know now that P2 is not principal. So, hence the ideal class of K, ideal class group of K is isomorphic to Z mod 4 Z. Okay. All right. Yes, so we looked at a couple of examples today, one of real quadratic field and one of imaginary quadratic field. In both cases, the ideal class group turns out to be Z mod 4 Z, and you see you have to work a little bit harder in the case of real quadratic field, because the group of units is infinite, right. There are many more elements with small norm. If you consider norm of elements in imaginary quadratic field, it is a square plus something positive times b square, and so norm keeps on increasing as a and b increase. So there are only finitely many elements of a given norm, whereas this is not true at all for real quadratic fields. And so usually you will see that you have to work harder for real quadratic fields, and it is precisely the same reason why proving things for real quadratic fields, class numbers of real quadratic fields, is much harder. So we will continue with examples again in the next class. Thank you.